Hi, welcome to Dissolve Chemistry. So let us continue our discussion on this equilibrium. So in the previous video of this equilibrium, we have discussed prerequisites for the study of equilibrium, and followed by that we have discussed definition of equilibrium, and we tried to understand what is the meaning of equilibrium, and later we classified equilibrium into various types. Okay, so that is physical equilibrium, and then chemical equilibrium and ionic equilibrium, like that we have classified. So in this video we are going to discuss, so what are the conditions under which this equilibrium is being established. Okay, and second important point that we will discuss is the equilibrium involved in the physical processes. Okay, so let us start with this. Conditions for attaining equilibrium. The important point is the process or the reaction must be reversible. Okay. So what do you mean by this? The reaction or the process must have tendency to occur in either direction. Either direction meaning is what? Now suppose, for example, if you take a reaction A plus B combines to give C plus D, then C plus D must have, if we call this as product, okay, and these as reactants, then these products must have the equal tendency or the tendency to combine back to give A plus B, as A plus B are having tendency to combine and form the C plus D. Means both must have tendency to interconvert into one another. Similarly, you can take some physical processes. Okay, say for example, I can convert ice into water. Okay, and water into ice. Means what is the meaning of this? We can interconvert both ice to water, water to ice, water to water vapor to water. So like that we can interconvert. Means reversible is most important aspect, either it is process or reaction. And second point we will take out. Second point is, of course, if the process is reversible, still if you carry out in an open vessel, so then establishment of equilibrium will be difficult, or it is not going to attain. Okay. So for that we need very important aspect is that to observe the equilibrium, the process or the reaction must be carried out in a closed vessel. Okay. Now what happens if you carry out in an open vessel? The question arises. So now suppose if you are carrying out in an open vessel, then what happens? Say for example, I have taken water, right? It vaporizes and it will be having vapor form over it, and there is a vapor pressure which is going to exert on the surface of the water. Now what happens? So the number of molecules escaping into vapor form and number of molecules condensing back, okay, if that becomes equal, then we call it as there is a dynamic equilibrium between water and water vapor, we can call. So now what happens if you keep it open? Then what happens? The water vapor formed will escape into the surrounding or in larger space. So when they escape into the larger space, okay, so then what happens? The equilibrium concentration of the vapor form will be reduced. So reduction of that leads towards shifting of the equilibrium in that particular direction, and evaporation goes on, increases, or the process will occur from liquid phase to the gaseous phase. Okay, reverse is not possible. So therefore we cannot observe, or it is not possible to attain an equilibrium under such situation. Similarly, now if you carry out in a closed vessel, what happens? You can see. Okay, so now the vapor form will be what? It is not having any option to escape out. So now what happens? So now you see initially the vaporization increases, then after that what happens? Some of the molecules start condensing back into liquid phase. Okay, So now what happens, the time when the number of molecules escaping and number of molecules condensing back becomes equal, then we call it as what? It is going to attain an equilibrium. So therefore, if you keep it in a closed vessel, then only it is possible to maintain the pressure and the temperature constant, and where we can observe the equilibrium. Fine. So that is very important. And third and foremost important condition, that pressure and temperature. Okay. Pressure and temperature also plays very important role. Okay. If we maintain the pressure and temperature constant, then only the equilibrium will be established and it remains. Okay. Otherwise, what happens, if we vary the temperature, then what happens, equilibrium may shift in either direction, maybe in the forward direction or maybe in the backward direction. So then you cannot observe the equilibrium as a stagnant or constant. Okay. So therefore, maintaining pressure and temperature is also very important, or we have to maintain the constant one. Okay. So let us move on to, so now we will discuss the equilibrium in physical processes. In that, so here we are going to discuss regarding the equilibrium established in phase transitions. Phase transition meaning is what? So interconversion, or between the two phases, like solid to liquid, liquid to gas, solid gas, like that. So between the two phases, whatever the equilibrium is established, so that we call it as equilibrium between phase transitions. Okay. First we will talk about the phase transition, equilibrium between solid and liquid. Okay, we will show like this: solid, liquid. Okay, and very important and a very common example we will take here to illustrate this. Okay, so that a equilibrium established between ice, that is solid water, and liquid water we call. Okay, or we can also represent like this: H2O solid, okay, H2O liquid. We can write like this. Fine. So now suppose to visualize the equilibrium between water and ice, so let us take the piece of a weighed amount of ice. Okay, so let us take in a isolated or like thermos flask. What you do, you assume this as a thermos flask. Okay, in that what you do is you take a known weight of ice, and now what we are doing is you have to maintain the temperature 273 Kelvin and pressure 1.013 bar pressure you have to maintain, and at this temperature and pressure your ice starts melting. Okay, so this ice will melt and you will be getting a what, liquid water over the surface of this. Hence with time what happens, the weight of the ice decreases and amount of liquid water increases. Initially it increases, and after certain interval of time, so the quantity or the amount of liquid water and amount of solid ice is going to remain constant and it will not change with the time. Okay. So and this point we call it as what? An equilibrium is being established between ice and water. Now at the equilibrium, what exactly happens? At the surface, lot of activity is going on at the interface. Interface means solid and liquid. Okay, so where exactly they are contacting with each other. So there what happens, the number of molecules in the liquid phase are going to condense back to form the solid state over the surface of the ice. In the meantime, what happens, number of molecules are escaping into the liquid phase, and as it is same, rate of getting into the liquid phase, rate of molecules getting into the solid phase, as it is equal, because of that reason only the quantity of the water and quantity of the ice is remaining constant. Okay, so that is what how we are going to explain the equilibrium between solid and liquid. And this happens at a particular temperature, that is 273 Kelvin. There is no net absorption of heat is going to take place here, and so your pressure is 1.013, or you can call it as 1 atmospheric pressure. So it is going to occur. Okay, and now we can what we can call this as, at the same temperature you have liquid water as well as solid water. What that temperature we call it as what? It is the melting point of that ice, okay, or that particular solid. So how we will define this melting point here? Okay, and if you alter the temperature, then equilibrium will shift in a particular direction. If you decrease the temperature below 273 Kelvin or 0 degrees Celsius, then equilibrium will shift towards solid phase. If you raise the temperature beyond 0 degrees Celsius, then your equilibrium will be shifted towards liquid phase. And exactly at the 0 degrees Celsius, equilibrium concentration remains, or both the phases are going to coexist. Okay, so therefore we define this melting point as, okay, at atmospheric pressure. Okay, the temperature at which both solid and liquid coexist is called melting point or fusion point. We call it as what? Fusion point. And we must remember that the equilibrium is dynamic, means the lot of activities taking place at the surface, means escaping of the molecule into the liquid phase, getting back into the solid phase. Okay, so that activity is continuous. Okay, it is not stagnant. Okay, I hope you have understood the equilibrium between solid and liquid. Next we will move on to equilibrium between liquid and vapor phase. Okay, to understand this, again we will consider water and water vapors, or we will mention like this: H2O liquid, H2O gas. Okay, so to understand this one, what you have to do, you assume that, okay, you keep the facility of measuring the vapor pressure. You take a known amount of water, okay, and keep it in a closed vessel and maintain the temperature constant. You can take any temperature, like we will take room temperature, say for example 25 degrees Celsius, or we can take it as 298 Kelvin. Okay, so now what happens? The number of molecules at the surface will escape into vapor phase. You take a vacuum flask, in that you take known quantity of water when you place, then what happens? Immediately the evaporation of water will occur. As the evaporation of water starts, okay, then what happens? How we notice that one? By measuring the vapor pressure. The vapor pressure goes on increases due to increase in the evaporation at the beginning. So that vapor pressure goes on increases. What is this vapor pressure? The pressure exerted by the formed vapor over the surface of the water, that is nothing but vapor pressure. Now after certain interval of the time, the vapor pressure becomes constant. When you are maintaining the temperature constant, then vapor pressure becomes constant. and that particular point we call it as what? There is an equilibrium being established between the vapor phase and liquid phase. What is that point we call? So now, as the number of molecules are escaped out into the vapor phase, now what they are doing? They are also condensing back to the liquid phase. And the time or the state at which what happens, the number of molecules escaping into the vapor phase, say for example, initially 100 molecules are coming out into the gaseous phase, you consider. Later what happens, it goes on decreases as the vapor pressure rise. And at a certain point what happens, the number of molecules escaping, say for example 10 molecules are going out into the vapor phase. In the meantime what happens, 10 molecules will get into the what? Liquid phase or condense back to liquid phase. What happens, the vapor pressure becomes constant. Okay, why it is constant? Because exchange is occurring with the same rate from the liquid to vapor phase to liquid phase. Okay, and that particular point where we can say is the equilibrium is being established, we can say that one. Now similarly, when this vapor pressure, the temperature at which the vapor pressure becomes equal to atmospheric pressure, or we can call it as what? If the vapor pressure is at 1 atmospheric pressure, the temperature at which it is going to happen, so that we call it as what? Boiling point. Okay. At atmospheric pressure, the temperature at which both liquid and vapor phase coexist, then that temperature we call it as what? Is called boiling point. That's one point. Another thing is, now suppose if you take different liquids, say for example, let us consider that we are going to take a equal volume 3 flask we will take, and in one we will take ether, okay, and another we will take acetone, okay, and in another flask we will take water. Okay, so now same quantity of all these three are being taken in 3 different flasks and all are maintained with the same temperature. The interesting point is that, so we expect that all must have the same vapor pressure. It is not true. Okay, so all the liquids undergo evaporation and they will be having their own vapor form over its surface. Okay, but the amount of vapor phase is going to vary from liquid to liquid at a given temperature. Okay, so now you can, as you got with an idea that what might be have happened with this. So all are maintained with 25 degrees Celsius. Okay, so now let me know that. So which is having greater vapor form at a given temperature? Obviously your ether will be having greater vapor form when compared to your water and acetone. What is the reason for that? Because it is in its inherent property that it is more volatile, we call. As it is more volatile at a given temperature, its vapor form will be greater, and if you keep it in an open vessel, it will evaporate readily even at room temperature when compared to the water. Okay, so therefore its vapor pressure is high at 25 degrees Celsius when I compare with water, compare with acetone, and acetone is having higher vapor pressure than compared to your water. So meaning is what? Vapor pressure at a given temperature for different liquids will be different, and it is going to depend upon the nature of that liquid. Okay, and the boiling, which is having higher vapor pressure at a given temperature, meaning is what? It is a low boiling liquid we call. Okay, so that liquid is said to be low boiling liquid. So these points you have to make note in the liquid and vapor phase equilibrium. The equilibrium between solid and gas phase. Okay. To understand this, what you have to do is you take, we call it as what? Directly conversion of solid to gaseous phase, we call it as what? Sublimation. Okay, sublimation we call. Now, there is a dynamic equilibrium is established between solid and gaseous phase. Okay, for example, you consider iodine. Okay, solid iodine you take, solid. Okay, so and then you keep it at a particular temperature like 25 degrees Celsius, right? Then what happens? It is a dark brown color solid it is. Now what happens? It starts fuming out, or the gaseous, the molecules are going to escape into the gaseous phase from the solid phase. So then how we observe this one? So this can be observed by increase in the brown color. Okay. So initially it is very faint, and later what happens? It goes on, increases thickness of the color or concentration increases. Okay. And at a certain point what happens? The color of the flask remains constant. Its meaning is what? The vapor iodine in solid phase and iodine in gaseous phase are at equilibrium. Meaning is what? The number of molecules escaping from solid phase to the gaseous phase, number of molecules getting back from or condensing back from gaseous phase to the solid phase is equal, and that particular point we call it as what? An equilibrium is being established between these two. Not only this iodine, there are many subliming solids like naphthalene is there, camphor is there. So these are all going to establish an equilibrium where we can see that at equilibrium solid and gas phase both are going to coexist. Okay, so this is all about solid and gaseous phase equilibrium.